thank you all for attending today's webinar. I'm excited to talk about joint design and layout. All right, so before we get into all this, I always like to start with a little history and a little background. First off, why do we even joint concrete pavements? Why are we doing this? So the first reason, and one of the most prevalent reasons, is that concrete shrinks. There are a few different mechanisms by which this happens, either drying, thermal, or chemical shrinkage. All of these mechanisms, all you really need to know is that concrete shrinks. It loses water during hydration, it cools off during hydration. The hydration reaction is actually very exothermic, but as that heat is actually given off, our concrete shrinks. And then our chemical shrinkage, the reactants in our chemical reaction for hydration, actually take up more room than our products, which is the concrete. So based on this, the concrete wants to shrink. Now, shrinkage itself isn't really an issue, but shrinkage plus restraint is. Now, if we build concrete pavements on a frictionless surface, say on Teflon or something like that, our shrinkage wouldn't be an issue. The concrete would just shrink and it would be happy as a clam. There wouldn't be any problem. But we build our concrete on subgrades and subbases. Now, those subgrades and subbases are resisting that the concrete's will to shrink. And when it does that, that's when we introduce stresses into our concrete, and those stresses eventually exceed the tensile strength of our concrete, and that's why we get cracks. So another big reason on why we joint concrete pavements is because of curling and warping. Now, these curling and warping stresses, similar to our shrinkage stresses, will eventually build up enough that we'll actually get cracks in our concrete. So the main thing is that when the concrete cracks is what we're trying to control with our joints. So a natural cracking pattern with concrete pavements is for the initial crack to take place somewhere between 40 and 80 feet. So that initial crack helps alleviate that initial buildup of stress. But then as the life of the pavement moves on, the stresses continue to build up, and eventually you get cracks about every 15 to 20 feet in both the longitudinal and transverse directions. So all of that's helping to alleviate the stress that's been building up through all of those forces that we just talked about. So now if we didn't do anything about it, we'd get a bunch of random cracks in random places, but we placed joints, we either saw them or we formed them, or we placed construction or contraction joints into our pavement to kind of control where this cracking is happening. So this is one of the biggest reasons why we actually put joints in our pavements. So some other reasons we actually put joints in our pavements. The first one, divide pavement into construction lanes or increments. If we're building a pavement that's 48 feet or 50 feet wide, we can't do that very well in one pass. So what we'll have to do is come in through in multiple passes. So we're basically giving the contractor the ability to actually pave this thing easily. And so those passes create joints in between the different paving lanes. Another reason, we need to accommodate slab movement. Now, the slabs, each individually, want to expand and contract with the weather and with moisture and those temperature and the curling and warping forces that they all want to act, all those slabs want to act independently. So we need to accommodate that a little bit to be able to make sure that they can relieve stress the way they need to so that we don't get more cracking. Additionally, we need to provide load transfer via dowels. So in this case, it would be extremely difficult for us to not joint a pavement and then come back in and place dowels. It would be a lot more difficult than it is to place our dowels during the paving process. So we joint pavements so we know where to put those load transfer devices. Additionally, we joint pavements for providing a uniform sealant reservoir. This is to help keep moisture and incompressibles out of our joint system and out of our pavement system. If we didn't have the joints there to form that uniform sealant reservoir, then the incompressibles would go into those random cracks, and it would be a lot harder to seal all those cracks since they're all forming randomly. Now, I mentioned that the longitudinal joints can help with paving lanes, but I didn't really say that they were for lane delineation. Now, this is how we use joints quite often, actually, but it should be noted that they're not actually for lane delineation. This is a good case. This picture provides a good example of one case where they didn't use the joints as the edges of our lane. So you can see here our center line is not where our joint is, and when we have tires come across here, when they approach the joint or when they approach the center line, they're not riding up against the joint. They're actually straddling the joints when they're going north and southbound on this road. So it's just another good thing to think about when we're thinking about designing our joints and where we're placing them throughout our paving process. All right, I also like to go through a little bit of the history of how we got to modern practice. I think it's important that we know why we're doing the things that we're doing now and what happened before that. What did we try before that either didn't work, or what did we learn? So when we started building concrete pavements, what we really did, we built about 6 to 8 foot squares, and they were all about 6 inches thick. And now this was really controlled by how much concrete we could produce at one time. So our actual mixing process was what was limiting the size of our slabs. So that wasn't really a big deal. We didn't really have a structural design, and really the purpose of these roads were to get out of the mud and prevent rutting, so we could have our precursors to our modern day roads. And for that it worked pretty well, but as we started to get more and more roads and vehicles started evolving, we started having increases in speed, and people started noticing that those joints were a bit rough and they weren't really the funnest thing to drive on. So they were trying to look for a way to reduce that roughness, and additionally we were starting to produce concrete more quickly and more efficiently, so we were being able to place more and more at a time. So we wanted to move from our construction joints, say building one slab at a time, to something where we could build multiple slabs at a time and use some kind of joint or crack in there to kind of serve as a construction flat surface joint. But now the issue with those cracks is they started to open up, and when we opened them up, we lost that long-term load transfer, and we also lost that smooth ride. So we kind of took a cue from a structural engineer's book, and we said, let's throw some steel in there to help restrain the slabs and hold those cracks tightly together. So based on subgrade drag theory, we calculated that there needs to be about 0.2% of the cross-sectional area in the form of steel. And that steel will help control or help keep those cracks nice and tight so we can maintain that load transfer. Now we're still constructing our slabs in 40 to 100 foot sections, mainly based on our production capacity. So remember though that concrete wants to crack in about 15 to 20 foot increments. And that's due to that shrinking, curling, and warping forces. And so it's still going to crack within that pavement, but those cracks are held tightly together by that steel. Now this is known as jointed reinforced concrete pavement, and it started around 1913. All right, so we had these cracks occurring at about 15 to 20 foot increments, and they kind of presented a maintenance problem. They were still somewhat random, and they're kind of difficult to maintain. So to control the cracking, we decided to go and actually saw the joints into the pavement at intervals of less than that 20-foot increment that it wants to crack at. So this way we had these nice straight lines that were a lot easier to deal with, to maintain, and that crack would propagate straight down from the bottom of the saw cut, and we would still get the aggregate interlock below the saw cut to get some load transfer across the joint. Now this was the beginning of our modern day jointed plain concrete pavement that's really common today. Now it differs from jointed reinforced in that there's no reinforcing steel holding all of those cracks nice and tight. And again, we were still constructing in about 40 to 100 foot increments as well at this point. So the next step that was introduced was to get more load transfer in between these construction passes. So we were building roughly 100 foot slabs. We needed some load transfer in between those slabs. You can see here that obviously this flat butt face joint isn't going to have a whole lot of load transfer with the next slab. So we started introducing dowels, and that was for that load transfer in there. And we also introduced dowels in our jointed reinforced concrete pavement. Now the contraction joints, so these joints still didn't have load transfer in them. We were still relying on aggregate interlock. In the jointed plain sense, in the jointed reinforced case, we still had that steel in there to keep those tight and make sure the aggregate interlock lasted as long as possible. So later on, we would start doweling all of the intermediate contraction joints, and this was in the 1920s or early 1930s. And eventually we got to the standard that we have today, where we have a fully doweled jointed plain concrete pavement. So the doweled jointed reinforced concrete pavement, though, before we jump to the fully doweled jointed plain, the doweled jointed reinforced didn't quite perform the way that we wanted it to. So our next step, as our structural engineers would note, was to put more steel in it. So we increased from about 0.25% steel for our jointed reinforced case all the way up to 0.75% steel by area. And so this was the beginning of continuously reinforced concrete pavement, and this was in the early 1920s. Now the increased amount of steel actually significantly increases that restraint that we talked about earlier. If you remember, that restraint and the shrinkage is what results in cracking. So we've increased our restraint, so the pavement wants to crack at shorter intervals to relieve some of that stress. And so our crack interval is reduced to about 2 to 6 feet. And that's because of that additional steel in there. So now these cracks are really, really tight cracks. They're like hairline cracks, and so they're being held together very tightly by all that steel and making sure that we get good load transfer. And so this worked actually pretty well. Another thing that we tried throughout the years was something called a hinge joint design. And this was a combination of dowel bars and tie bars, or rebar, placed in the pavement at different intervals. And so the idea behind this was that you'd have dowels for your flat butt face joints, or your construction joints, and you would have rebar or you'd have rebar or tie bars in your hinge joints to make sure that this joint stays tight and you get good aggregate interlock. So the combination between the two were supposed to work in tandem, such that you would get good load transfer all your joints. Now, this worked relatively well, but the issue is its constructability can be kind of chaotic because you have to keep track of which joint has which mechanism for load transfer. So it didn't really catch on. So we were left with our three main pavement types: our jointed plain, our jointed reinforced, and our continuously reinforced concrete pavements. Now this chart has got a good summary of all the different characteristics of these pavements. The one that I'm really going to point out to you, though, is that as our transverse joint spacing increases, our transverse crack spacing decreases. So as we get over here all the way up to CRCP, where we don't expect any when we don't have any joints, we are expecting our cracks to be at shorter intervals. When we have our joint spacing at a very small interval, at our 15-foot typical joint spacing, we're not expecting any cracks in our intermediate panels. Another thing to briefly note, jointed reinforced has kind of fallen out of favor. It's not really covered in our current designs of Pavement ME or Darwin ME design, as it was known a few years ago, and it's not really used in ACPA's street pave design. You can design it with AASHTO 93, but it's really fallen out of favor. To illustrate that further, you can really see here, jointed plain concrete pavement has really kind of become the dominant concrete pavement within the United States. The slide's a little bit old, but the trend is still pretty much true. There are only a few states that really do continuously reinforced. I know Texas is left off of this chart, but they also do a lot of continuously reinforced concrete pavement. And I know the Illinois Tollway is also looking to do some as well. Now, the reason CRC has kind of fallen out of favor isn't because it doesn't perform well. It actually performs very well. It's a very low maintenance and long life pavement. It's just it has a very high upfront cost because of all of the required steel to make sure that those cracks are maintained and are as tight as possible. That ends our history lesson for today, but now we can move on to the types of joints, and I've kind of thrown these out as we've gone, but now to catch everybody up, for those of you that don't know, we'll kind of breeze through these pretty quickly for all of our different types of joints. So there are three basic types of joints that encompass about 99% of the joints constructed, and these are our contraction, our construction, and our isolation joints, and we'll go through these all briefly. Also mention expansion joints in a little bit as well. Now, each of these types of joints can occur in the transverse or longitudinal directions. There are also some specialty joints, and these are mainly for transitions or terminal joints in our pavements, and we'll cover those briefly as well. So our most popular type of joint is our contraction joint. These are our typical sawed joints. And when these occur in the transverse direction, these are the joints that we saw as we're kind of going along and paving our pavement. So these occur every about 15 to 20 feet in the transverse direction, and about every 12 to 14 feet in the longitudinal direction. Now notice that these have that aggregate interlock below that saw cut, and it doesn't have a smooth butt face joint that we will see in the construction joint. You can see here illustrated we've got a doweled and an undoweled form of joint, and that's really going to depend on your traffic level and what your pavement design is, whether or not you're going to have dowels in there. You'll also notice that the saw cut is somewhere between 1/4 and 1/3 of the thickness, and your dowel is placed below that at about half mid-depth of your pavement. So the other type of contraction joint or saw joint is a longitudinal contraction joint. Now these occur if you're paving, say, 24 feet, or if you're paving about 2 lanes at one time. So in that case, you're going to place a saw cut at that center of that section that you just paved. So now these also can be untied, so you can have no reinforcement as we see in the top case here, or you can actually have a longitudinal tied joint. And the reason we put a tie bar in there isn't for load transfer like our dowel bars, but it's actually just to keep that joint tight and make sure that our lanes don't drift apart from each other. So next up are our construction joints. Our transverse construction joints, these are also commonly known as headers. These occur typically at the end of a day's paving run, or if we have to interrupt our paving operation for some reason, if there's an emergency. This is where we'll see a transverse construction joint or a header. Now these can be formed or sawn. You can see here we've got a case in the top right where we've got a formed construction joint. You can see here down at the bottom left we also have forms placed for this construction joint as well, and that's most likely so we can handle this in-pavement object here separately from our mainline paving. You can see here they actually just ran the head of concrete out, and they actually put down a mat there so they could come in here, saw this joint, and then take off that head of concrete and start paving right there the next day. Now in the case where you pave through your head of concrete and you saw the joint out, you'll have to come back in and drill your dowel bars in if you're going to use dowel bars. You also know occasionally we've seen it where you actually use a tie bar in those construction headers. That's not typical, but it has been done on occasion. So when we are resuming paving at a header, there are a few guidelines. You really just want to make sure that you have a smooth transition from one to the next. And one of the main ways you can do that is by making sure that you take 6 hours before you resume paving at that header to make sure you don't run into any issues. Alright, so similar to our transverse construction joints, our longitudinal construction joints have that smooth surface between the two paving sections, and these occur when we pave one lane and then we say we come back and pave another lane, similar to what's shown in the picture on the right. You can see that the pavement on the right was placed first, and we came back and we placed that second run of pavement. Now these especially, it's very important to have a tie bar in there to make sure that those lanes stay together tightly and to make sure that we don't get them drifting apart. You can see down in the bottom left we've got that deformed tie bar, and then we also have a keyway. Now keyways are something that we've tried, and it was a kind of this novel idea where you basically form in a section that would fit into the other side of your joint. So you'd have a male section, as you see here, and a female section on there, and they fit together, and you get some load transfer there. Now in theory it seemed like a decent idea, but there were a few problems with it. The first off is it's not very easy to construct. Concrete doesn't like being constructed with those, well, at least our slip form paving concrete doesn't like to be paved with that little protrusion in there. The other issue is that concrete inherently doesn't perform as well in tension or shear, and that's the main mechanism that we were hoping to get load transfer here. So this section of concrete is actually just going to shear off right at that edge there. So for those reasons, keyways, they didn't really work out the way we wanted to, and they're not really recommended, and they're not really in use much anymore. So those are our construction joints. Next up is our isolation joints. Now, our transverse isolation joints are typically used at bridges or at intersections or small in-pavement objects. We'll get to those a little bit later. We'll also get to intersections a little bit later. As shown, the transverse isolation joints, they might have a thickened edge, and that's to compensate for there not being any load transfer in there. You can also put a dowel with an expansion cap in there. That way they're still isolated, but you still have some load transfer. We've tried sleeper slabs to aid in supporting those free edges and basically stiffening up that last slab. Our longitudinal isolation joints, as you can see there, are typically for when you're paving next to a fixture or a structure. If you're paving next to a building, we want to make sure that our pavement movement doesn't impact the building or, say, a sidewalk or anything like that. We want to make sure that they're kind of isolated from each other. The bottom right picture actually shows a good case of where you have a header next to an isolation joint. That isolation joint is actually from a roundabout where they're trying to isolate the approaches from the circular portion of the roundabout. And we'll mention that a little bit later as well. So years ago, it was common practice to place transverse expansion joints in jointed reinforced concrete pavement. And that was on the interval of 300 to 500 feet. And this was really because in theory that 300 to 500 foot section was going to expand and then they were going to impact each other. Practice actually degraded the performance of jointed plain concrete pavement because when you add that additional space in there, what ends up happening is your slabs start to migrate apart from each other and basically have bigger gaps at your construction and contraction joints than you would want. So basically that extra gap that you live in there as the expansion joint eventually gets filled up by all of your other joints. So it didn't work quite as well, and so for that reason expansion joints aren't really recommended. Now some people use isolation and expansion joints interchangeably. They're not really the same thing. It's really just kind of a difference in nomenclature sometimes. When people are talking about expansion joints, a lot of times they just mean isolation joints. There are a few times where you actually will use expansion joints. On that you can kind of look at our proper use of isolation and expansion joints in concrete pavements. Occasionally they are actually still used on bridges, and you can actually see here's a great picture of it. You can see there's actually like a 4-inch gap in here between our pavements, and then you have these steel teeth that kind of cross the barrier to make sure you can go from one section to the other. So that's what a typical expansion joint looks like as compared to our isolation joints, which are typically about a 1/2 inch to 1 inch wide. All right, so now we get to move on to some of the specialty joints, and these typically occur at transitions and at the end of pavement runs. So the main ones are transitions between concrete and asphalt. You can see here that a lot of times what we end up doing is relying on a thickened edge to make sure that we stiffen up that joint a little bit and get decent load transfer from our concrete to our asphalt section without any big jumps. So we've tried the thickened edge, and that seems to work well. A few different scenarios of that, one without a dowel, one with a dowel, one where the thickened edge is actually extended a few feet. We've also tried extending the concrete under the asphalt a little bit, and that also seems to work. That also can work well. A dowel is a good idea in there to make sure you maintain load transfer into that concrete section over here. So next up are terminal joints in our CRC. So this is when we're transitioning from continuously reinforced concrete pavement to one other type of pavement, or if we're getting to a bridge. The most common form of joint on this is the wide flange steel beam. It's kind of a lug and anchor joint design. You can see here what we have is we actually have a steel beam that's placed in concrete that's encased under our CRC pavement. And so that steel kind of serves as the bridge from our CRC section to whatever is on the other side. And that CRC section is actually extended under the beam there. So this provides the continuously reinforced pavement to actually, it provides room for it to expand and contract independently of that other pavement without causing any damage to that other pavement. And that the steel beam is actually held in place very well by that anchor down there. I've actually seen this same type of method used in a jointed plain concrete pavement. An agency was worried that they were paving on a hill, and they were worried that the grade was so steep that the pavement would actually just kind of fall down the hill, and so they actually used an anchor joint where they kind of had concrete piers protruding down from the bottom of the pavement and then steel up for the piers into the concrete to kind of hold the pavement in place. It wasn't really necessary, but they were really concerned, so they tried it. All right, so now we know our different types of joints, and I've mentioned quite a few times now that our joint spacing is typically somewhere between 14 and 20 feet. Well, how did we arrive at that? How did we get to maximum joint spacing? What's really ingrained in that? Well, our typical method for calculating joint spacing, well, at least in the mechanistic term of things, so when we're looking at the actual properties of the materials, is based on the radius of relative stiffness, and that's the equation that you see here. That radius of relative stiffness is based on our modulus of elasticity of the concrete, the slab thickness, the modulus of subgrade reaction, and a Poisson's ratio of the concrete as well. And so our way of limiting the stress within the concrete to an allowable joint length is by limiting the ratio of our joint length, the big L, to our radius of relative stiffness, little l. We found that through observation that a ratio of 7 works in the field, but we tend to limit it to about 4 to 5 to be conservative when we're designing things. So if we go through an example, you can see here if we have a modulus elasticity of our concrete of 4 million psi, a thickness of 8 inches, K value or our support constant, so that defines our support layer, of 100 psi per inch. It's pretty weak, but there it is. And a Poisson's ratio of 0.15, if we calculate that out, our radius of relative stiffness is about 36 inches or about 3 feet. So now you multiply that times that constant, the ratios that we said we wanted to limit that ratio to 5 or 7 in the field, you get about 12 feet or 15 feet, which was very typical for what we would see in the field. So about 15 feet for our joint spacing. So now there is an easier way, and you'll notice that if you actually look at this equation, there are 2 variables in there that don't change a whole lot. Our modulus of elasticity is always going to be around 4 million psi, and our Poisson's ratio is usually going to be about somewhere between 0.15 and 0.2. So if you break this down, it actually turns into a pretty easy empirical equation where our maximum length between our joints, our ML, is equal to our slab thickness times the support constant. And that support constant is based on how stiff or how rigid your support layers are, your subgrade. And if you have a subgrade or an unstabilized granular subbase, you're going to have a higher support constant than if you used a stabilized subbase like an asphalt-treated base or cement-treated base, lean concrete, or anything like that. It's going to be more rigid, and so that support constant is going to go down, so your maximum joint spacing is going to go down. If you don't really want to remember those support constants, there's an app for that. If you go to apps.acpa.org, you can find the maximum joint spacing calculator. It's a free app. It's really easy to use. You basically just put in your thickness and define your layer immediately below the surface, and it'll spit out your maximum joint spacing. So a few other recommendations for our maximum joint spacing. We've already talked about that we want to limit it to about the thickness times the support constant, but we also want to maintain about a square shape or a rectangular shape. We don't really want to exceed an aspect ratio of 1.5. And what I mean by that is if we have, if the width of our slab or the width of our paving lane is 12 feet, we wouldn't want to exceed 18 feet in the transverse, in our transverse joints. What we found in the field is that square actually does work best, but obviously that's not always practical for what we're trying to pave. And our rectangular joints actually work pretty well. In some areas, we actually have seen that longer joint spacings do work, especially when they have a good handle on their materials. If they're using a low coefficient of thermal expansion aggregate, that'll lead to less shrinkage and better performing joints. Iowa is one state that has done this a lot. They've been known to use 18-foot joint spacings quite often and gotten good performance out of them. But to further emphasize the effect of joint spacing on your design, you can actually see this this graph here. This is results straight out of AASHTO's Pavement ME program, and you can see that as our joint spacing increases, our predicted slab cracking increases as well. And you can see it's pretty significant once we get past about 17 feet. That increase in slab cracking is very evident. You can see that 20-foot joint spacing getting all the way up to 80% slabs cracked for that high traffic. So if we go back to here and we look at that equation at the top, the maximum joint spacing is equal to our thickness times our support constant. You can kind of guess that our thickness can be very closely related to our maximum joint spacing. And there is actually one program that's tried to leverage this, and that's TC Pavement's OptiPave program. The main idea behind that is that if you limit your joint spacing, you can actually reduce your thickness of your concrete. And they've paved this quite a lot. South and Central America, Guatemala and Chile actually do this quite often, and They've seen good performance out of it. It hasn't really caught on here in the U.S. In fact, I don't think that there's actually been a section paved using this design method in the U.S., but it's something to keep in mind if you're considering looking at different design options. Another way we kind of utilize this idea of controlling our thickness by using different joint spacing is when we talk about overlays. Now, I'm not going to spend a whole lot of time on overlays due to time restrictions today, but if you do want more information, I encourage you to look up the Guide to Concrete Overlays, the 3rd edition from the CP Tech Center. It's a free document. You can download it at their website. It covers just about everything you may want to know about concrete overlays, especially when it comes to the joints. So getting into the overlay joints a little bit, one of the ideas is to reduce the slab sizes so that we can reduce the thickness, and when we do that, we're basically limiting the flexural stress within our concrete. The stresses building up from our shrinkage and our curling and warping aren't quite as high as, say, our standard slabs. In addition, a lot of times we're also relying on our underlying layers, especially if we're using a bonded overlay. One of the ways we're having a thinner section is by utilizing that support layer as part of our pavement. It helps reduce the stresses within our slab. So you might think, why shouldn't I go shorter and shorter with my joints? Well, a big reason you wouldn't want to do that is because of the location of the joint within your wheel path. Now, that can be a major issue if you have your truck traffic driving right on your joints all the time. You're probably not going to get very good long-term joint performance. Additionally, when you have 2 foot by 2 foot slabs, that results in a heck of a lot of joint sawing. So, a few reasons why you don't want to do it. So when we're thinking about our joint design, especially in our overlays, you may want to consider where your traffic is actually running on this pavement. You can see that 2 foot by 2 foot example, you've got the wheel path right on the joint. So if you play around with it a little bit, go to 3 foot by 3 foot or some 4 foot by 4 foot or even 6 foot by 6 foot joints, you can really play around with where that joint is relative to where your wheel path is. And that 6 foot by 6 foot joint kind of actually illustrates that picture that I showed earlier where our paving lanes were not, and our longitudinal construction joints weren't used to delineate traffic. We actually had a joint in the middle of our driving lane. You can see that in the 6 foot by 6 foot case. We've actually moved the wheel path away from right on the joint as we would typically see it in a typical 12-foot lane where our longitudinal construction joint is right on the center line of the pavement. To illustrate the idea of having the joints in the wheel path, it can be a bad idea. This is just a picture of one of our overlays that was built in, I believe, Minnesota, and it didn't perform well mainly because those joints were right in the wheel path. Similarly, actually here we actually had a section that debonded from the asphalt beneath it, and we got some joint deterioration there as well. So some basic overlay jointing practice summaries. It really kind of depends. Your joints are going to depend on the type of overlay that you're doing, whether it's bonded or unbonded, especially if you're doing bonded concrete overlay on concrete. Those have some specific joint details and joint requirements that you'll want to look at before considering doing bonded concrete on concrete overlays. But for your conventional unbonded overlays or your bonded concrete on asphalt overlays, your joint spacing is kind of what you would expect, where the smaller joints, the smaller section will require smaller joints. You can see here for a less than a 3-inch overlay, which isn't typical, we would typically use something like 3 foot by 3 foot joints. 3 to 6 inches, you may have 4 by 4 joints or 6 by 6 joints. And when we get into 6-inch overlays, we're typically going to be somewhere around conventional or using that 6 foot by 6 foot joint spacing. All right, so now we're going to talk just briefly about joint sawing and joint sealing a little bit, but it's good to have some kind of conceptual idea about when we're actually performing the sawing and sealing to actually create our joints. So the main thing when it comes to when to actually saw our joints is this conceptual idea of the sawing window. And this window is defined by when the concrete has gained enough strength to resist raveling, and when our stress within our concrete actually reaches our strength in our concrete, which is when cracking is going to happen. So in between there is our sawing window. We keep this as a conceptual idea rather than defining times to this because it's so dependent on a variety of different factors. The first being the environment. What kind of weather are you having? Is it sunny and hot, or is it cold and rainy, or is there a lot of moisture in the air? All of these things can affect that sawing window and when those bounds are kind of reached. Additionally, the subgrade and subbase, whether it's high friction, low friction, or whether it's got a whole lot of moisture in there, or whether it's free draining, all of those can impact it as well. Additionally, your concrete mixture, what's actually in your concrete, is going to play a big part in it as well. Is there a high demand in concrete? Is your hydration reaction going to occur quickly or slowly? What kind of fine aggregate are you using? How much fine aggregate are you using? All of that will play a role in that sawing window as well. Additionally, if you're paving against existing lanes, those existing lanes may actually draw moisture out of the pavement that you're actually just paving, so that can actually alter your sawing window as well. Saw blade selection plays a big part in this as well. If you have early entry saws, you can obviously get on there and saw that joint earlier. We'll talk about that a little bit more in a few minutes. And curing. Curing is another big thing that has a huge impact on our sawing window, and the reason for that is when we properly cure our pavement, what we're trying to do is trying to keep our moisture and our temperature within our concrete. The reason for that is that's what's going to help drive our hydration reaction. So when we keep that moisture and we keep the temperature in the pavement, it's helping our hydration reaction, and that's what's going to develop the properties of our concrete that we want, the strength, the durability. That's really going to help make our concrete as good as it can be. So to illustrate what that does to your sawing window when we're curing our concrete properly, what's actually going to happen is it's going to develop our strength faster. We're going to get better strength more quickly, and it's also going to delay the onset of that internal stresses. That hydration reaction is going to be going the way we want it to. That stress development is going to be delayed a little bit. So you can see how that sawing window is actually changed quite significantly when we have proper curing of our pavement. So there are a few different tools that can really help you kind of define when that sawing window is and when we should be getting on there. One of them is the evaporation rate calculator. This is another free app on our app library. Basically, it takes your environmental factors combined with some of your concrete factors, and it basically defines how much moisture you're losing from your concrete over the course of time. So since we don't really have a way of truly defining the joint sawing window, there have been a lot of different things that have been tried. A lot of times a good experienced sawing crew will have the best idea of when it's okay to get on there and start sawing the joints. We've tried a lot of different things, from just scratching the surface with a nail or a fingernail, or really anything, just to see how it reacts to that cutting, or to predict how it's going to react to the sawing of that joint. So to illustrate this, if we get on there too early, what's going to happen is we're going to get that unacceptable level of rattling there up on the top. And that's just because our concrete has not reached an acceptable strength where it can resist that sawing action. Once we've waited a little bit longer and it's gained enough strength, we get into the moderate level of rattling. You can see there that actually looks pretty good in terms of our joint. When we get down to no rattling at all, down at the bottom of that picture, then we're actually getting to the point where we're going to risk that random cracking happening. We're getting to the point where your concrete built up a lot of strength, but there's also a lot of that internal stress buildup from our shrinkage and our curling and warping stresses. So we want to be somewhere around that moderate to none range. We definitely don't want to be on there too early for the unacceptable range, and we don't want to wait too long that we get some cracking. So one tool that's actually very useful in helping define that when to get on the pavement and actually start sawing our joints is Hyperpave. Now this was a program developed by the Federal Highway Administration. It's a free tool. You can download it at hyperpave.com. I believe we also link to it in our app library. But it's a really useful tool. It predicts that early stress development and the strength gain based on the actual environmental factors as well as the material factors, basically what our mixed constituents are that are going to drive that hydration reaction and that strength development. Okay, so that's just a little bit on when to get on there and start sawing our joints, but that's not the only piece of the puzzle. The other part is saw cut depth. We have to make sure that we actually initiate the crack at the bottom of that saw cut to get our early forming joint. If we don't saw our joints to the proper depth, what will end up happening is the pavement doesn't want to crack where we want it to crack. It's going to crack wherever it feels it'll best alleviate the stresses that have built up within the pavement. You can see here on the left we've got a good example of a longitudinal crack that developed just because our joint wasn't sawn to the proper depth. On the right, I've highlighted where that's actually cracking and where our joint was sawn, but you can see that it's definitely not where we actually want it. And you can see the crack's actually propagated over here, and it's not on that saw cut where we want it, where we would have liked it to be. So typical recommendations for our saw cut depth for our transverse joints, we're typically going to saw them at 1/4 to 1/3 of the thickness, depending on if you're on an unstabilized or stabilized base. And that's because with a weaker base or a weaker subbase or subgrade, that crack is going to be more likely to propagate, and it's going to propagate more easily than on a stiffer subbase like an asphalt or a cement stabilized subbase. So that's why for those we need to saw the cut a little deeper to make sure it's propagating where we need it to. The reason you don't want to saw cut too deep, and you don't want to go T over or 1/3 of the thickness on all of your transverse joints if you don't have to, is that we're still getting some aggregate interlock, and you get more if you have a thinner saw cut. For the longitudinal joints, we're typically going to saw those at T over 3 just to make sure there aren't any problems. We're not really looking for good load transfer between those. We're not looking for good load transfer between those joints. We're really just trying to make sure that they stay tight and stay where they're supposed to be. And we really need to make sure that the longitudinal joint activates the way it should, because as we saw in that previous slide, the longitudinal cracking that can come off there, it's typically going to end up right in a wheel path and be very detrimental to our pavement performance. So we've already talked about timing, how timing is a factor. But with early entry saws, you can notice that a lot of times it's playing on the mechanics of the materials, and so you can get on there a little bit earlier and you can actually saw those a little bit earlier. And that way you're still getting a significant amount of aggregate interlock. So the limits on those are typically going to be around 1/5 to 1/6 of the thickness of the pavement, but you never want to be less than 1.5 inches, or 1.25 inches, excuse me, because you really need to make sure that that crack actually does propagate. If you do start to see some dust kicking up, that means that your strength is developing a little more quickly than you'd like, and that also probably indicates that your stress development is going a little bit quicker than you'd like, and you really want to make sure that you alter your sawing pattern to about 1/4 of the thickness to make sure you activate the joint where it's supposed to activate. So now all of this is a lot more complicated than our typical recommendations. It's from a lot of field experience, a lot of testing, testing in the lab, a lot of computer simulations, finite element analysis, fracture properties of the material. All of this has gone into modeling of the saw cuts and how the crack's actually propagating, but it's basically kind of encompassed in those recommendations on the previous slide. You can see here, actually, this is a great picture of how an early entry saw. It cuts very thin cut into our pavement, and it activates right where we want it to. We've tried a bunch of different methods for activating contraction joints. You can see on the top left there that pizza cut, basically a pizza cutter type roller, our typical conventional saw. You can see on the top right that an old version of a span saw. You can actually see here down at the bottom right, we've actually tried where we put something on top of our dowels and have the crack actually propagate up from our dowels to make sure that we're our dowels are in the right place, but we don't have the necessity of actually coming in and sawing the joints. Now, it was a decent idea, didn't quite work the way we wanted it to, though. So our main types of joints are our typical conventional walk-behind joint, or walk-behind saw, excuse me. Our early entry saws are used a lot as well. Span saw isn't quite as popular as it once was, but you still see them on occasion. So when we're talking about our saw blades, most common are the industrial diamond and the abrasive saw blades, but we really need to match your proper application. Basically, different aggregates are going to have different hardnesses, so you really need to match the saw blade to your concrete. Manufacturer's recommendations really kind of define what should be used and when it should be used. Just a note on the order of your saw cuts. Common practice is to cut those transverse joints first. And you almost always want to cut them in the order that they've, in sequential order. People have tried doing skip sawing where they saw every second or third joint just to kind of save time to get on there and make sure you get some of that early stress development alleviated. But there are some issues with that. What can end up happening is if you're doing skip sawing, you can actually create dominant joints, and those dominant joints may open up wider than all of your other joints, which can cause a problem. So if possible, you always want to saw them in sequential order. So once you're done with transverse joints, you can come back in and cut your longitudinal joints. And one thing you do want to, as a sawing crew, you definitely want to be checking your depth. You want to make sure that you're not too shallow, because you want to actually create that weakened plane and make sure that your crack happens where you want it to. You also don't want to be too deep, because then you're putting in an additional effort that you don't need to, and additionally you're reducing the amount of aggregate interlock that you have on at the joint. And as your blade diameter decreases, obviously you're going to have to adjust your thickness as that blade actually wears down. Alrighty, so now we can move on to joint sealing. Again, like joint sawing, we are going to kind of go through this very briefly since it was already covered in a couple webinars back, but I just want to give you a brief little background about it and kind of some design recommendations for different types of sealants. So you got to start off with what sealing is actually for. Sealing is for minimizing the infiltration of surface water and incompressibles into our joint system. So we're trying to keep out moisture and trying to keep out those incompressibles that can actually degrade our joint. Now, it's not to completely prevent this, because we can never completely prevent moisture from getting into our joint system. It's just not possible. So that's kind of the definition of joint sealing and what we're trying to do with sealants. Now, some states have moved away from sealing joints, but there has been some very promising research. I know Dr. Dan Zollinger down at Texas A&M University has been doing a lot of research on how joint sealing can impact erosion. It's been shown that it can definitely help your pavement performance overall, and it's definitely something that you don't want to completely neglect. If you are sealing joints, however, they need to be maintained throughout the life of the pavement. You don't want to seal your joints and then leave that sealant in there for longer than it's recommended or for longer than the life of the sealant. You are going to have to replace it at some point within the pavement's life to make sure that it's performing the way it wants to perform. What can end up happening is you can get, once the sealant reaches the end of its life, it can actually start letting in water. It can also let in incompressibles, and then it doesn't have a place to evaporate out to. So if you have seals, make sure they remain sealed. Okay, so when we're sealing our joints, the first thing that'll happen is we'll go through and we'll do our initial saw cut, as we can see here on the left, and that's a pretty thin cut, and then that crack propagates where we want it to. If we're sealing our joints, we come back in and we saw our sealant reservoir. And on the right, this is for field poured sealants. What we'll end up doing is putting a backer rod in there. The reason for that backer rod is to make sure that your sealant isn't adhering to more than two surfaces. So we've got the left wall, we've got the right wall. We don't want the sealant to be on the bottom as well. What will end up happening is if we're sealing to 3 surfaces, that crack will actually propagate up straight through our sealant. And so we're trying to avoid that as best we can. Additionally, by having that backer rod in there, you don't need quite as much sealant. So when you are using field poured sealants, it's important to know your depth to width ratio. And this will depend on which kind of sealant you're using. You can see here some typical recommendations for hot poured sealant, silicone sealant, and 2-component material cold poured sealant. These are all you're gonna want to know what the manufacturer's recommendation is for that sealant, and that's what you're gonna want to abide by when you're using that kind of sealant. In addition, there are also preformed sealants. This one here on the left is an example of a 5-cell compression seal. And the way that one's going to work is it's actually going to stay in compression throughout the life of it, throughout the life of the sealant. That's just how it's designed, and that's the way it's going to keep out the moisture and the incompressibles. We also have joint sealants for isolation joints as well. You can see here you will want to use a bond breaker beneath whatever compressible material you're using in between that isolation joint, and then that sealant material is there on the top. Okay, so if you are sealing your joints, it's really important to make sure that the joint surface is clean. This is one of the most important things that you can do when you're sealing your joints. If you don't have a clean surface to adhere to, then your joint seal isn't going to perform the way it's meant to perform straight off the bat. So it's really important to make sure you either wash it with water, or if you blow it out with air, make sure that those surfaces are clean for the sealant to adhere to. So it's really easy to check whether or not your joints are clean. You can see here, you can just wipe your finger against it and see whether or not that surface is actually clean. But again, it's really important to do. There are a few apps on the web or on our app library related to sealants: the joint movement sealant elongation estimator, the compression seal joint width calculator, and also our joint noise estimator. So all of these are good free resources you can find at apps.acpa.org. All right, so now we can move on to load transfer, and I've kind of mentioned this throughout the webinar so far on what the different mechanisms are for load transfer and what's actually happening with them, but we'll go through them a little bit here as well. All right, so our main forms of load transfer are aggregate interlock, which we've talked about, and our mechanical connection in the form of dowel bars, and then sub-base support. You can see here, that's a great picture of that crack propagating down from our saw cut, and you can see how the maximum aggregate size would be important, because the larger the maximum aggregate size, the more it's going to protrude onto the other side of that joint. So it's definitely something to consider when you're thinking about aggregate interlock as your form of load transfer. When you talk about dowel bars, we'll actually talk about dowel bars as we go through. Additionally, sub-base support, it's not typically what you're relying on, but it can contribute some to your load transfer. However, I would warn you that messing around with your sub-base support for the sake of load transfer is definitely not something you want to do. You'll end up creating consequences for yourself that you shouldn't have to deal with. All right, so one big problem with the joint system itself is that we don't really design, we don't really have a dowel bar design. We have a standard spec that we use, and that's typically about it. Same thing goes for tie bars. We don't really design them. We don't really check anything. We basically just use standard specs that we've always used. And in recent years, in the last, since we started using dowel bar retrofit in the 80s, we've kind of seen that we can actually move away from this standard spec and start kind of designing these a little bit more. So it's definitely something to think about, and I'll touch on that a little bit more in a few minutes. But a few of the main reasons we need that load transfer efficiency, especially when we're thinking about dowel bars, is for two main reasons. One of them is pumping, and the other is for roughness. Now, roughness is pretty much one of the main ways we improve roughness of the joints is by using dowel bars, but pumping is another monster entirely. For pumping to happen, we basically have to have four things. We have to have undoweled joints, or they have to have extremely poor load transfer. We have to have water, we have to have fast-moving heavy loads, and we have to have fine-grained material. So now what happens is those fast-moving heavy loads actually pump up water and fine-grained material. So if you eliminate the water, then you don't have anything for the fine-grained material to travel in through the joint in that pumping action. And if you don't have fine-grained material that's erodible, then you don't have anything to erode. So this whole pumping action can really erode your support system and basically destroy your joints. So the main way that we combat this is through doweling our joints and making sure that we have proper load transfer. So again, we typically don't design our dowel bars, but we do have some basic recommendations, and that's basically based on your pavement thickness. The thicker the pavement, the thicker the bigger diameter dowel bar you'll typically need. You can see here when we're in the 8 to 10 inch range, we typically see 1 1/4 inch dowels, and we get above 10 inches, we're gonna mainly see 1 1/2 inch dowel bars. Now, I keep saying cost difference on here because in some areas where you're typically manufacturing 1 1/2 inch dowels, they may actually be cheaper than 1 1/4 inch dowels. If you have 1 1/2 inch dowel where you're supposed to have 1 1/4 inch dowel, you're actually most likely going to get better performance, and that's what we've seen from pavement ME analyses, and finite element analysis as well. If we're in the 7 to 8 inch range or less than 7 inches, typically you're not going to have enough heavy loads to require dowel bars. Additionally, it can be difficult to place dowel bars when you get into really thin pavements. And pavement ME has also shown that 1 inch dowel bars perform significantly well. You actually get a really huge jump when you go from 1 inch dowels to 1 1/4 inch dowels in terms of performance. So there are a lot of different types of dowel technologies. There are a lot of emerging technologies as well. You can see here there are a lot of different forms of plate dowels that are coming out, a lot of different materials for dowels. Plate dowels have actually kind of been used a lot in industrial floors. We've seen them used a lot there. Occasionally they have been used in pavements as well. But there are a lot of different materials that are evolving our dowel designs as well. So one of the reasons that this has been brought on is when we have long life pavements, we need to start thinking about what kind of materials our dowels are made out of to make sure that they don't erode. We want to make sure that our dowels can outlive the life of our pavement, especially when we get into 50-year design life. If we have an erodible dowel in there, that can lock up our joint and ruin the performance of the joint. So we need to make sure that we match the dowel to the application as well. And there are a lot of different types of these that have been developed, and these long life dowels have performed very well, and some of them don't have significant increases in cost as well. So if you're designing a long life pavement, it may be something that you want to consider. So I said that that we don't really design our dowels very well, but there are a lot of design options that we can use. They may not have been quantified, and they may quantify in the form of lab experiments, but we do have a lot of different options that we've seen used in the field and seen different performance with. So you can see here the diameter, the length, which kind of project it is. There are a lot of different options when we're looking at our dowels. In addition, there's also a lot of different options when we're talking about our dowel baskets. Now this is in case you're not using a dowel bar inserter. If you're just using conventional baskets, there are a lot of different options for the basket itself. You can see the list there. One other mention on the dowel baskets when we're talking about when you're placing dowel baskets, some states actually require you to cut the shipping wire. We've actually had studies that prove that you can leave that shipping wire intact, and you can actually see, or it can actually help you in your placement of your concrete, making sure that that dowel basket remains rigid through the paving process and you don't have any issues with that. So leaving the leaving the shipping wires intact is definitely something that you may want to consider in the design stage, or allowing the contractor to do that. Another option, there are different types of leg styles. You can see the J, the U, the V, the choked V, and there are also different types of coatings on our dowels as well. From epoxy coating, which is our most common one, red oxide paint, Tectol, plain steel, stainless steel. They're all different kinds of dowel bars that we've used and seen decent performance. Now, the coating thickness required by various states, and I mentioned epoxy coating is the most common thing used. So all the different states have different recommendations and different requirements, and you can see here they range from all the way down to 5 mils all the way up to 18 mils up in New York. So you can see that there isn't a whole lot of uniformity here, and one of the things that I've been really looking to try to move towards is kind of a standardized design. And you can see that this was kind of a standardized choices based on the National Concrete Consortium's recommendations and published by CP Tech Center. If you want to look that up, again, that's another free resource on CP Tech Center's website. So another good thing to do. One thing that I will note on here, though, is the dowel doesn't have to be exactly at mid-depth of your slab. It can be in the middle third of your slab, and you can still get similar performance. And that can help, especially when you're about standardizing your dowel baskets. It can be a lot easier and can be actually cheaper to manufacture and buy those. So just something to think about. For our dowel spacing, this is what I was talking about when I said that we don't really design these. The standard has kind of developed into having 12 dowel bars per 12-foot wheel lane, having those at 12-inch spacings and 6 inches off of the edge. Now, through dowel bar retrofit in the 1980s, we've kind of seen that you can reduce the number of dowels and still get similar performance. So basically reducing cost by reducing the number of dowels that you need. So if you actually come in here and you remove some of these dowels in the center of the lane where they're not really doing much good, you can actually some significant money over the course of a project. This has actually also been studied using software called DowelCAD. This is another free software. I believe it's linked to from our apps library. And this can kind of analyze different dowel configurations. You can see if you eliminate some of the dowels, you can analyze the bearing stress, the edge stress, and the deflections. You can also analyze what happens if you move a dowel away from the edge of the pavement. So the reason you may want to do this is so to reduce the risk of the edge of that edge dowel actually being clipped by the paver. All right, so one thing that has kind of been evolving a lot in the last 10 years is how we ensure steel alignment within our pavement. We've used GPR, Mira scanner, and then the one that's really caught on lately is the MIT scan, and you can see that there on the right, the guy pulling that box along that joint. And when you do the MIT scan, you get the readouts, kind of the heat signature maps there, where it basically shows you where the dowels are. And then based on where those dowels are, you can define the horizontal translation, the vertical and longitudinal translations, and the tilt and the skew. And based on all of that, you can get what's called your joint score. Now that joint score is something that is relatively new, and some agencies have really been trying to limit the joint score. ACPA has actually developed a guide spec for dowel bar alignment, where we're trying to standardize this to make sure we don't run into a situation where a lot of different places have their own recommendations. Now the thing with this joint score is it's a pretty new thing. We basically have just been able to quantify what's going on in the joint with our dowel bars, but we don't really know what that means. So here's a case where we actually had a section where we had some pretty bad joint scores. The higher the joint score, the worse our dowel alignment is within our joint. So you'd expect something like this to a project that has these joint scores, you'd expect your joints to be in terrible shape. Well, this is actually done, this study was actually done on a 30-year-old section down in Georgia. You can see this was at 30 years, it still looks pretty good. Your joints look in pretty good shape. So we're quantifying this joint score, but we don't really know how it's really impacting the pavement. So it's just something to consider. So our tie bar design is kind of similar to our dowel design in that we aren't really designing these things. It's really based on subgrade drag theory, which isn't really good enough to kind of design these things. So there has been some research going on. ARA published a study that we've kind of developed into our ME tie bar designer app. It's another free tool on the website. And this can help you determine which dowel bars to use at what spacings. So one note when you are talking about dowel bars and spacings, you may actually want to leave the tie bar next to your transverse joint out. The reason for that is you don't want to lock up the joint. You can see here's a case where the tie bars are placed directly next to our dowel bars, and what's going to happen there is you're not going to have any freedom of movement with your dowel bars, and they're not going to be able to transfer the load because that joint's going to just lock up. Okay, so moving on, I just want to briefly mention if one of the things that you're worried about is long-term joint durability, or if you're having issues with that, CP Tech Center does have a few good resources that you can look up. These are all free on CP Tech Center's website, so they've done a lot of research on joint performance and kind of looked into what are some of those problems. Alrighty, so now we can move on to joint layout. I'll try to be brief with this and kind of go through some of these topics. Let's get into it. So just some reasons you may want to consider concrete intersections, roundabouts, is really just their durability and their long-term performance. They really kind of do hold up a lot better than, say, our asphalt counterparts. When we get all that dynamic loading with the truck stopping and starting, you're not going to get any rutting with the concrete pavements. So when we're thinking about intersections, roundabouts, interchanges, we really need to consider the thickness, the jointing, the traffic management, whether or not you're going to use fast track mixtures because you need to expedite the building process, and there are a few other considerations as well. Now, we're going to focus on the jointing. I will mention a couple things about thickness design because remember, thickness and jointing can be pretty closely related as well. So your thickness design should be based on the AASHTO methods or street pave or the PCA method, some kind of conventional thickness design pattern. But when you're thinking about an intersection, you need to think about what kind of traffic you're going to get in that physical area. So I've highlighted the physical area here. Obviously, we have two roads intersecting. Well, that physical area is going to see the traffic from both of those areas. So you may want to consider actually adding a little bit of thickness in that physical area if you have two high volume roadways intersecting. If you have a low volume road intersecting a high volume road, the thickness of that high volume road is going to be enough to carry that little extra load from the lower volume road. But if you have two very high volume roads, that's when you may want to consider adding a little bit of thickness. All right, so getting into joint layout, there are a fair amount of rules that I'm going to go through in a little bit, but it can be summarized down to this. Keep it short, keep it uniform, keep it perpendicular, keep it simple, and keep it practical. So if you keep those 5 things in mind, when you're thinking about joint layout, you're really going to get the best performance out of your joints. So let's get into it. If we're talking about intersections and actually roundabouts as well, the things that we want to do, we want to match our existing joints and cracks. What I mean by that is if we're building onto an existing section, we really want to make sure that we have the same type of joint. So if you're adding a right turn lane and you have an isolation joint in your existing pavement, you want to match it with an isolation joint. If you have a crack in your existing pavement, you're probably going to want to put a joint there because otherwise you'll get sympathy cracking in your new pavement. So just another thing to consider. We want to meet our in-pavement structures. I'll mention that, or I'll go through that again in a little bit. Remember that maximum joint spacing that we talked about. Place isolation joints where needed. We'll talk about that again as well. One big thing for agencies and engineers to remember is that what's in the field may not be what's exactly on the plans. And that means that the contractor has to adjust to what he sees in the field. So the contractor really needs some leniency to be able to adapt to what's out there. Additionally, if you actually get a contractor involved in the early stages of the joint layout, you'll probably get some good feedback on what's practical and what should be done which way. So some things to avoid: we definitely want to avoid odd-shaped slabs. We don't want to be too small, we don't want to be too big, we don't want to have too many sides. When we get into those odd-shaped panels, those are the ones that are most prone to cracking. We also don't want to have sharp angles. We don't want to have anything below 60 degrees if possible. Typically, our square joints are better. So the 90 degrees, you can see there on the top picture that we've got a really acute angle, and that's where it's going to want to crack to help alleviate that stress. You can see there in that middle picture, that's a very odd-shaped panel. If they would have just added an additional joint in there, they could have prevented that crack from happening. We also want to reduce the amount of interior corners that we have, but occasionally, again, you have to violate these rules on occasion. So based on those rules and recommendations, ACPA developed a 10-step method of jointing. Step 1, we start with our bird's eye view and we draw in our back of curb lines and our edge of pavement lines. Step 2, we add in circumference return, taper return, and crossroad return lines. We want to offset them from the edge of our pavements anywhere from about 1.5 feet to 3 feet off of the edge of our pavement. You'll see why in just a minute. So next we draw our lines for our mainline roadways. We extend those all the way through. We don't cross our circumference return or our taper return lines. We do cross our road return lines though as well. So you'll notice here that we kind of deviate from that angle right at that crossroad return line. And that's where we start going straight. And that's going to help prevent a sharp angle from occurring right there where this line meets this line. So next, we want to think like a contractor would think, how do I actually want to pave through this? If I can use a slip-form paver through this intersection, it's obviously going to be a lot easier than placing it by hand. So define your main line lanes for paving. So next up, step 5, we add transverse joints wherever our width of our pavement changes. So you can see here, wherever you start a curve, you're going to add in a transverse joint. You can see this one's from this side, this one's from this side, so we add in our transverse joints at our width changes. And once we do that, we can add our transverse joints outside of the central area of the intersection. And here we want to keep in mind our maximum joint spacing, and we want to try to keep our joint spacing as uniform as possible. So next up, we extend the edges of the pavement lines from the crossroad, and we kind of define our intersection box. You notice there that intersection box is looking pretty good. You can kind of see what we still have left. We have just between the intersection box and where the pavement width changes left to joint. So what we're going to do is we're going to check that against our joint spacing. So with step 8, we check the distance between our intersection box and our closest transverse joint. And if that's greater than the maximum joint spacing, we'll add a joint. If it's not greater than our maximum joint spacing, we will alone. And again, we don't want to extend these lines yet through our circumference return or our taper return lines, because what we're going to end up doing is in step 10, we're going to deal with them to try and make a panel that won't crack. We're still going to have some odd-shaped panels, but we have a few methods that will reduce the potential for cracking. So this 10-step method, it really kind of reduces the amount of panels you have. You're still going to have some. They're kind of unavoidable, but there are these few tricks that you can do that will kind of result in the best performance that you can get out of it. So you can see here a few different places where we try some different things, especially here with B, where you'd have a sharp corner coming through here. You can kind of add a dog leg in there and kind of make it perform the way you want. A few different ways to handle this odd-shaped panel here. You can either do what they did here and integrate it into this slab and make it a bigger slab, or you can do what happened over here, where you cut it off and then you integrate it in with the curb. A few different ways to handle those things. Occasionally you'll run into a dead-end joint or have some interior corners, and there are a few different ways to handle this. You can see here on the left we have an interior corner. So what we're going to end up doing is throwing a couple rebar in there, and what's going to happen then is if we get a sympathy crack in this section over here, the rebar is there to hold that crack really tight. The other option is we can form a hole in there, or we can core a hole in there, and that'll alleviate the cracking as well. So one example of that is here. They actually put a form in there for that dead end joint. You can see they paved over it, and it ended up like this. So now with that hole, you're not going to get cracking across here, or cracking up through there, or through there. You're not going to get sympathy cracking in those panels. And then you just come back in and fill up that hole with some kind of repair material. So last thing to note with our intersections is we need to adjust for utilities. This is one of the critical things doing with this. We really need to make sure that we adjust for those, because a lot of times we do see them in our intersection, and it's something really simple to do, but if you don't do it, it can kind of lead to some poor looking joints. So adjust your joints to meet those in pavement structures as best we can. A few box out details here. Having an isolation joint, if you do have sharp corners, you may want to still think about adding some reinforcement to make sure that you don't get sympathy cracking in there. Notice a few different ways to handle an inlet as well. The only place where we're not going to really see an isolation joint is a telescoping manhole, because they don't require them. So if you do box out properly, if you handle these in pavement structures as best you can see that you can get some pretty good joints, and these will perform well for a long time. If you don't consider them and you don't box out properly, what's going to end up happening is you're going to get some cracks. And you can see here, this is similar to this one. The bottom picture here is similar to the top right picture in this slide, in that all we would have had to do is put a joint right there, right where that crack developed, and it would have performed just fine. Now the reason it's cracking there is all of this concrete is trying to shrink back to the centroid of this slab. And so this doesn't have a clear way to do that. So when you're thinking about joint layout, think about how your slab is going to contract to the centroid of your slab. So then you can look at the edges and where your issues are going to be. You can see here they could have easily adjusted this joint over to the inlet, and also probably added an isolation joint around it. Here could have adjusted this a few different ways and not ended up with a few triangular slabs and an interior edge that's just going to become an issue as well. So just kind of think about these things, and when you see them, there are a bunch of different ways to address them. You can see here it's not always pretty, but there is the jointing plan may look a little silly, but there are good ways to handle this to get proper performance. If you do have good practices, you can see that you can get good performance. This is actually on a curve. You can see that contractor actually put a stake in there for the sawing crew to aim at, and got a good looking joint. Similarly on the right, going exactly to the center of the radius of the center of that circle for that curve. This method, this joint layout method for intersections, it works for nearly all intersections. You just need to make some adjustments when you have some crazy things like wide medians or dual left turn lanes. It also works for a variety of different things. This is a parking area. It's really just helping minimize the amount of odd-shaped panels that we have and finding a way to deal with those as best we can. Similar method works for cul-de-sacs. I'm not going to spend a whole lot of time on this, but you can notice that we do have as many square panels as possible. A note on isolation joints. These are used a lot when we talk about intersection to isolate one approach from another. The idea being that if we have a long concrete roadway here as it expands and contracts, if we have an isolation joint there, it's not going to impact our intersection here. So just a few, it's a good place to have an isolation joint. When you are doing a joint layout, it's probably a good idea to map out which joints are going where. And if you're a designer trying to do joint layout, it's always good to get contractor involvement and see how they would lay it out, because they're the ones that are going to build it, and they've dealt with all of this in the field before. All right, so now we can move on to roundabouts really quickly. The intersection method doesn't work as well for roundabouts, mainly because if we do it, we end up with something like this, and then when our traffic comes through here, we're hitting all of those joints at strange angles. Additionally, it doesn't really lend itself to guiding pedestrians through the roundabout. So jointing it like an intersection isn't probably the best method. So there are two main methods, the isolated circle and the pave-through method, which I'll go through very briefly using this six-step method. So what we end up with is these two jointing plans. If we remember our rules from intersections, all of those still apply. So step one, we start with our bird's eye view and our back of curve and edge plans. Step two, we're going to decide if we're going to want an isolated circle or a pave-through method. You can see here we've isolated the central part of the roundabout from all four of the approaches. In the pave-through method, if you have a big enough radius, you can actually get a slip-form paver in through here to pave that, which can be very helpful. And this also helps guide traffic through here if you have one direction that's more dominant than the other. So step three, you add your transverse joints within the circle. Keep in mind the maximum joint spacing on the outside edge because that's where it's going to be critical. Step four, we add in transverse joints wherever the width changes. Step five, we fill in the transverse joints between those width changes and with that, and extending out of the intersection or out of the roundabout. And step five is also where we deal with some of those odd-shaped panels. Again, we're not going to completely eliminate them, but we can reduce them as best we can. And then in step six, we adjust for those in-pavement objects, those fixtures, and we adjust for those odd-shaped panels. So that's the six-step method. You can end up with some good joint layout plans for either type of roundabout you choose. There are a few other methods. This one's actually called a pinwheel or a spiral method. It's more popular in Europe, and you can see how each exit leg kind of radiates all the way into the next exit leg, and it kind of goes all the way around in that spirally pattern. So if you do this well, you can end up with properly jointed roundabout. This is a good example of one from Overland Park, Kansas, just outside of Kansas City. You can actually zoomed in on this, and you can actually see where the joints are placed. And I looked at this, I think last year, and it was still performing pretty well. All right, so last thing I'm going to mention is diverging diamond, and I'm going to just jump through this real fast. This is something that we've seen come up a little bit more and more. This is this crazy interchange that we typically see in high volume areas. And the idea behind this is that to get on the highway, you're not crossing traffic. You have two main places where you cross traffic, but you're always turning into the roadway without crossing traffic. It also reduces conflict points, which is why a lot of traffic engineers have been moving towards it for some of these high volume areas. You can see what it looks like here as well. So the issue with this is jointing. What we basically have is we actually have a bunch of intersections combined into this one interchange. So this jointing method isn't this jointing procedure isn't completely finished, but we do have 11 steps that kind of walks you through this. That can get you a jointing plan for it. This will be up on our WikiPave site, and you can look at it more there. So I'll just step through this really quickly. We start with our bird's eye view, and then we separate it into 4 quadrants. And then we define those, we kind of cut off the edges of the 4 quadrants. We add in our circumference return and taper return lines for the outside. We add in a crossroad return line as well. And then we can define our paving lanes for the main line approaches. We don't want to cross that return line just yet in the center of the roadway. Then we can add in all our transverse joints radiating out from the center. And then we can start dealing with all of the other 4 exit lanes as well. We start with longitudinal joints, and then we add the transverse joints radiating out from there, and then we address our odd-shaped panels. The goal is to end up with something like this, and this is an example from the Illinois Tollway that they put together, and you can kind of see what the jointing plan looks like. This is another example of how to deal with that intersection. There is also something that's being tried. I believe this is being tried in Wisconsin, and please excuse my crude drawing. I haven't had a chance to perfect this one yet, but this is kind of similar to the pave-through method in pave-through method for roundabouts, you can see here one direction we choose paves all the way through, and then we would isolate this section so these approaches don't impact that central section. And I haven't had a chance to kind of deal with the odd-shaped panels that are going to come up in here, but you can see how that may be another way you want to approach this. So if you do go through these steps and you end up with a good jointing plan, you can see that similar to our other joint layouts, we end up with good solid joint plan, and we can get a good performing diverging diamond interchange. All right, so now just a few quick notes on troubleshooting. Just one, this is our last slide for the day. But if you do run into issues, there are a lot of resources out there, a lot of ACPA literature, a lot of CP Tech Center literature that deal with a lot of the issues that we've run into with pavement. So feel free to look out there for that. You can also look at our WikiPave site, a lot of the apps as we went through. Also, don't hesitate to call your local ACPA chapter or us here at ACPA National. We're always happy to help get you through any questions that you have with your jointing.